I'll take a look at an example now that's going to hopefully help you a little bit on your homework with one of the trickiest questions there. It'll require a little bit of thinking that's going to be perfect for those who will be going on to advanced calc next semester. So it'll be a really good warm-up for that. All right, so let's consider the sequence given by a sub 1 equals 9, a sub 2 equals 6, a sub n is equal to 1 over a sub n minus 1 plus the square root of a sub n minus 2. So we could do some examples of this if you'd like to get a feel for it, right? A sub 1 is equal to 9, a sub 2 is equal to 6. Now, a sub 3 is going to be 1 over a sub 2 plus the square root of a sub 1. So this will be 1 over 6 plus the square root of 9. In other words, this will be 19 over 6. And then so on and so forth. You would use previous terms to find more terms. We'd like to prove that 1 is less than or equal to a sub n less than or equal to 16 for all n in the natural numbers. What we're really saying about the sequence is that this sequence we're trying to prove is bounded. Bounded means that it's going to be between these two numbers, and it's never going to become larger than 16, and it's never going to become less than 1. So let's see, how do we prove that? So how we need to do this is we need to use induction. We're going to use induction. So our proof by induction, the first thing we need to do is the base case. So we have our base case. Now, our base case in this case is actually two base cases. We need to verify two initial conditions. We need to verify both of these are going to work within these bounds. So base case, we're going to say let n equal 1. So we have to start with the smallest natural number here, n equals 1. Notice here, is a sub 1, is that between 1 and 16? Well, yes. So notice 1 is less than or equal to 9, less than or equal to 16. So a sub 1, so 1 is less than or equal to a sub 1, which is less than or equal to 16. So that's your first base case. The next base case here, we're going to say let n equal 2. This should be a sentence. Well, let n equal 2. Notice that we have 1 is less than or equal to 6, which is less than or equal to 16. So 1 is less than or equal to a sub 2, which is less than or equal to 16. Great. We've now proved both base cases. If there was 3 terms here, for 3 previous terms, we'd want to do 3 base cases. All right, so now we have the base case done. Now for the induction hypothesis. So our induction step, we're going to assume that we have 1 less than or equal to a sub n less than or equal to 16. Assume this is true for n. Now, there's a little slight twist of this. What we're really saying is that it's true for n, but it's also true for things less than n. So it's true for n minus 1, n minus 2, and all of the previous terms, but we're trying to show that it's true for n plus 1. So normally you just need the previous term, but in case you have more than one, we could now use multiple ones. So assume this is true for all, or for n, and values less than n. We'll prove 1 is less than or equal to a sub n plus 1 less than or equal to 16. So this is our goal. We'd like to do this. Okay. So how we come up with this, as I think in the hint that I gave you, is we want to work with each of these inequalities by itself. We don't want to try to do all of this in one step. So what that means is I'm going to just work trying to prove that a sub n plus 1 is greater than or equal to 1. So notice here, a sub n plus 1 is equal to 1 over a sub n plus the square root of a sub n minus 1. So this is what my a sub n plus 1 term is. I want to show that it cannot be smaller than 1. So what that means is I'm trying to figure out when is this smallest and when is this smallest. So I'm trying, if I have two things that I'm adding, whenever they're the smallest, then that means that I indeed have the smallest total sum. So we're working with both of these. These numbers are between 1 and 16. So the smallest this can be, well, that's going to be when that actually is equal to 16. So worst case scenario, maybe that equals 16. That's as small as I can get. So I know that this must be greater than or equal to 1 over 16. So basically this is always less than or equal to this because 16 is always bigger than that. But then over here, when is this smallest? Well, this isn't smallest when it's big, it's smallest when it's in the other direction. So this is going to be also greater than or equal to the square root of 1, which this is obviously equal to 17 over 16. So a sub n plus 1 is always, followed inequalities, greater than or equal to 17 over 16, which obviously is greater than or equal to 1. So that is the smallest that can be. Now, on the other hand, I'm trying to figure out what's the biggest. Could this ever become bigger than 16? So also, we see that a sub n plus 1, which is equal to 1 over a sub n plus the square root of a sub n minus 1. What is this? What's the biggest these can be now? So this is going to be biggest when the denominator is the smallest. Denominator is the smallest when it equals 1. So this is going to be 1. And then this expression here, the square root, this is going to be the largest when the inside is largest. That's going to be when it's equal to 16. So I have plus the square root of 16. And so this is always less than or equal to 5, which obviously is less than or equal to 16. So great. So I've shown that a sub n plus 1 is greater than or equal to 1, and a sub n plus 1 is less than or equal to 16. So hence, we have shown that 1 less than or equal to a sub n less than or equal to 16 for all n in the natural numbers by induction. And that concludes the proof. So this is the idea, this is the intuition. Obviously, you have slightly different numbers, you have slightly different things to work with, but this thought process of how do I make these numbers the biggest or smallest when we know each of those numbers are in some type of assumed bounds. Like I said, this is going to become key to what you're going to be doing in the fall in advanced calculus. So if you do have questions on this, please let me know, but hopefully this video helps clarify kind of how you want to approach that homework question.